Okay, so next we're going to talk about formal charge. And this is going to be a tool that's going to help us out with our Lewis structures. So make sure you're comfortable with the introductory topic that I talked about before. I'm going to have a practice worksheet for that. Make sure it makes sense. I'll have a key posted with it. Because moving forward, our octet rule is going to become an octet suggestion. And I probably said that a lot in 221. I don't think I've said it in any videos in this class thus far. So this octet rule is going to get broken a lot. It's like trying to put a curfew on a 21-year-old. Good luck with that. That is a rule that's going to get broken a lot. They have a car and they can, buy alcohol legally. Good luck keeping them in the house. All right, after 10 p.m. or whatever. So, formal charge is going to be the tool that lets us A, figure out when we're going to break the octet rule, and B, figure out how we're going to break the octet rule. So, it's going to allow us to choose our best Lewis structure. There's going to be a little more detail about when we can break the octet rule. I'll get to that in a little bit. But we have a formula here. So formal charge is calculated atom by atom. So every single atom in a molecule is going to have a formal charge. And so this formal charge is going to be equal to the number of valence electrons. And we're going to subtract from that the number of non-bonding electrons plus 1/2 of the number of bonding electrons. So we have our non-bonding electrons. So these would be things like lone pairs. And these would be our electrons in bonds. And this is just straight up what the periodic table says the element has. So as an example, let's look at NH3 one more time here. Sticking with our ammonia. Oh, almost forgot my lone pair. Okay. So, if I look at the formal charge of a nitrogen with 3 bonds and 2 lone pairs, well, I have 5 valence electrons, and I'm going to subtract, I have 2 non-bonding electrons, and I'm going to have 1/2 times the number of bonding electrons, so 2, 4, 6. So 1/2 times 6, this comes out to be 2 plus 3, so this ends up being 0. So we have a formal charge of 0. Hydrogen making a single bond. Well, I have 1 valence electron according to my periodic table. I have 0 non-bonding electrons. And I have 1/2 times 2. There's 2 bonding electrons around this hydrogen. This equals 0. Now all of these hydrogens have the same configuration, so we get zeros across the board. That's good. That's what we want. And so that is just using the formula to calculate, and then we come through and we're like, oh yeah, so if I were to label formal charges, I could just be like, oh well, 0, 0, 0, 0. Okay. So nitrogen can't break the octet rule. Hydrogen can't break the octet rule. Only elements in the 3rd row of the periodic table. You have to have d orbitals accessible. So, octet rule cannot be broken by elements in row 1 or 2. You have to be row 3. So stuff like phosphorus and sulfur, they're going to break the octet rule like crazy. We're going to do some examples here in a minute. And you've seen this before. If you think about phosphate, PO4 3-. How do you get four oxygens around a phosphorus without breaking the octet rule? So nitrogen has to follow the octet rule. Oxygen, carbon, fluorine, boron, hydrogen, they all got to follow the octet rule. So they don't get to have fun. You need to have enough surface area around, enough space around the atom to do this, to fit more than 4 electron groups. And you got to have d orbitals accessible, so we'll talk about that more later. But for now, only row 3 and above are breaking the octet rule. So we'll do another example here. Let's look at sulfate. So SO4 2-, okay? Now, we have two situations here. So first off, well, here, let's draw the structures and we'll talk about it. So we've got a polyatomic ion. So you're gonna say, well, there should be no bonds, right? It's an ion. Well, I got bad news for you. It's held together by covalent bonds. So we have something like this. That'd be one option. Now this is gonna have 6 valence electrons from the sulfur. Each of these oxygens is gonna provide 6. Plus we have 2 extras. So don't forget about that. These polyatomic ions, we have more valence electrons than what the atoms themselves bring to the party, what the elements themselves bring. So we should have 6 plus another 4 times 6, so that's 30. We should have 32 valence electrons, so we have 2 extra to give that -2 charge. And so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32. Okay, we're looking good. We've got the right number. Oxygen is more electronegative than sulfur. It has all of the lone pairs. Everything's looking good. Oh, and this should be a -2 up here. Sorry about that. Or we have an alternate structure we could draw. What if it's sulfur and this one's going to follow the octet rule. We'll talk about how the one on the left doesn't in a minute. Okay, so this is also going to have 32 valence electrons present in the structure. I do the brackets with the -2 charge to show that this whole thing combined has a -2 charge. Now this one's nice. Look at that, sulfur, 2, 4, 6, 8 valence electrons around it, okay? What do we got over here? 2, 4, 6, 8, 10, 12 electrons around the sulfur. That 12 is not 8, that is not an octet, that is something different. So we're gonna have to talk about that. All right, so if we do the math here, we use our formal charge with the setup we have here. This oxygen is going to end up with 6 minus 2 minus 1/2 of 6, so that's 3, so it's 6 minus 5. So this ends up being a -1 formal charge, which means this one's a -1 as well. This oxygen, it ends up being a 0. This ends up being a 0. You can do the math, you can double check me on that. Again, just do the valence electrons, non-bonding, bonding, etc., etc. And then this sulfur in the middle, guess what happens? It's going to 0 out as well. That is a 0 formal charge. It ends up being 6 minus 6 because we have 12 bonding electrons, no non-bonding electrons. So 12 divided by 2 is 6. So we get 6 valence minus 6, which equals 0. All right. Now if we go over here, we get -1s on all of these oxygens, okay? And then sulfur ends up with +2. So all these green markers, these are for the formal charges, okay? And so we go, okay, under our old system, this would make no sense. This cannot be it. Under our old system, our last video, we go, everything has a complete octet. This looks good. Everything's good. What, it's obviously got to be the option on the right. Well, sulfur is in the 3rd row of the periodic table. It's not row 1 or 2, so it can break the octet rule, and oh boy, does it quite often. This right here is our best structure. So the structure on the left. That's our best structure because it has smaller formal charges, less formal charges. More of them are 0. Nothing is greater than a magnitude of 1. We have 2 -1s here, but over here we have a +2 and everything has a formal charge. So we're going to talk about the rules for using formal charge in a minute, but this is our best structure. because of formal charge. We're going to put those rules up in a minute. But this is what we use it for. So we are building on this idea of using Lewis structures. We have two competing Lewis structures. They both have the right number of valence electrons total, 32. If we can't break the octet rule, it'd have to be that guy. Turns out we can. So how do we know which one's better? We use formal charge. And that's what it tells us. All right, so let's talk about the rules we just applied here. So give me a second. I'm going to erase just the left side of the board. We'll be right back. All right, power of editing. How about that? Okay, so we're going to use formal charge to find our best structure. So there's three rules here. We're going to talk about them, and then we're going to come back to this example. We're going to talk about why the left structure is the one. With a little bit more detail, and the rules actually in play now. So you're not just watching baseball, but you actually understand the rules. You know, like, now you know why they don't just hit each other with the bats and then run around the bases as many times as they can. Like, there are rules to the game, right? So, smaller formal charges equal better. So that means 0 is the best. So -1, +1, it's just how far from 0 are we? We want to minimize that as much as possible. You see a formal charge of +5, rethink your structure. You see a +12, something went wrong. You know, or a -12 even, doesn't matter. You want to try to keep it as close to 0 as possible. So like this nitrogen one, they're all zeros. You can't do better than that. Or I'm sorry, this ammonia example here, all zeros, perfect. That is a perfect structure. Can't always get that. We'll talk about that more in a second. You shouldn't have like charges next to each other. So if you're going to have things with negative and positive formal charges, they should be interspersed. You shouldn't have a negative bonded to a negative or a positive bonded to a negative. And rule number 3, if you are stuck with negative formal charges on any atoms, they should go to the more electronegative species. So oxygen is more electronegative than sulfur because it is above it on the periodic table. So we want our negative charges on the oxygens, not on the sulfur. So that's good. We don't have any like charges next to each other. We don't on this one either. So rule 2 is obeyed in both of these possible structures. Smaller formal charges equal better. Well, we only have 1s and 0s here. We have 1s and 2s, and there are no zeros. So that is why this is the best structure. Rule 1 says this guy. Both of these follow rules 2 and 3 very well. But oftentimes rule 1 is going to be really what you lean on to find the best structure. So you want to minimize formal charges. And it turns out to do that, we break the octet rule. Now we can't do this with something like oxygen or nitrogen because they are in the second row, but we can do that with sulfur, and we do. So this is our best structure. All right, so just to be clear, we've got our -1s on our most electronegative element. We've got mostly zeros. Now, we can't have zeros on everything. Generally, our formal charges are going to add up to the total charge of the compound. We have a -1, a -1, 0, 0, 0. We add all that up, we get -2. We come over here, we got -1, 1, 1, so -4 plus 2, -2, okay? Up here, this ammonia, 0, 0, 0, 0, adds up to 0. NH3 has no net charge, it's not an ion. So that's perfect. Like in this case, we could potentially get all zeros. Sometimes you can't still, but if you see a polyatomic ion, you know there's going to be negative or positive formal charges in play. And so I'm going to throw up another practice worksheet, and these are going to be more complicated Lewis structures that you're going to have to use formal charge to figure out the best structure for. I will write a key. So again, it's not, this would be kind of the practice problems I do in class. This isn't part of the homework. It might help you with the homework. It should help you with the exams, things like that. But this is just kind of to fill in so I don't spend time on the board directly doing this. I can kind of push it off onto paper, and that's what I plan to do. All right, so next we're going to be talking about bond lengths, bond energies, and then I'll probably have a separate video for resonance. And that will be the end of the chapter. So we only have a few more topics left. But these Lewis structures are going to be incredibly important moving forward and through the next chapter. So make sure you practice them, make sure they make sense. If you have questions, use the forums on the Moodle page. I'll be checking those regularly. And odds are, someone else has the same question. So if you email me, that's great, that's cool. But to help me avoid getting 10 of the same email, I'm trying to use the forum system. So please help me out with doing that. You gotta ask the questions for me to answer them. Don't be shy. And if I screw something up, let me know. I'm generating a lot of new content for this class. I'm happy to fix any errors I make. So call me out, that's fine. Or maybe I didn't make a mistake. Maybe you did, we'll find out. All right, either way, I'm happy to get it settled. Okay, so this is the whole story on Lewis structures. And like I said, it's a very important tool moving forward. So that's what we're gonna do. All right.